right, so let me see what did I screw up here. So what I'm trying to get to is if the expected value of if this is true, then you should be able to take this term and cancel it out with the terms that are generated here, which is what's a concept known, which is that these terms are linearly independent. Why don't I go on and come back? That's actually the point that I wanted to get to, and I'm like having some trouble thinking through what I did wrong here. If someone has the right expansion of that to cause that to happen, that would help me out. So over here, if we're trying to compute the variance of this, all you really need to do is compute the expected value of x squared minus the expected value of x squared. That's equal to the expected value of x squared is 1 times p, and the expected value of and that's the expected value of x squared. And this is minus the expected value of x squared, which is equal to p squared. So that's equal to p times 1 minus p. That's the variance of x. And if we want to use that, which is that the two things are independent, then if you wanted to compute the expected value of x1 plus y1, if you want to compute the variance of x1 and y1, then you'd get that that's equal to p times 1 minus p plus p times 1 minus p, or 2 times that. Let me then move on to...
You could just write the general form of that variance of the sum and see the result.
Which is what you mean?
That's the variance of x plus the variance of 1 minus twice the covariance of x and 1.
Covariance of plus y. Oh, is that what actually? Did I do something wrong there? No. Okay. 2 times expected value. Well, why don't I come back to this and then I'll do this, because I want to get through the whole rest of the lecture. Sorry about that. And I think the point that I wanted to make before we'll finish this up and then I'll get back to that, which is that we're describing a set of I guess the next concept that we need to deal with is the notion of a probability density function, which is instead of doing masses at a particular point, which is a particular event, we're trying to talk about a set of events between a set of events where the set of events is an infinite set of points. In other words, if we think about a continuous thing that could range between 0 and 10, then the set of points that we need to describe with our density with respect to our probabilities might be everything under 5. So what's the probability that x is less than or equal to 5? That's basically, in the case of a probability density function, it's defined to be sort of the area under this curve. And the interesting thing there is that unlike before, where you had this thing where you could describe the exact probability at a particular point, if you tried to do that with every single point, then you'd be in a weird situation. And I think that so this becomes a more useful tool. And getting back to Neil's point before, which was what's the point here? The point is that with regard to masses and so on and so forth, here again we're using the word, the analogy again of density, and that's another thing that's in the physical world, which is there's a density associated with a particular object, and you can summarize it by putting it around a particular point. You can say actually that the probability for a really tiny piece is equal to the integral between this point and that point. and bring it down even smaller. But it's not it's not what's a good way of putting this? It's rarely the case that you want to talk about the probability of x is less than or equal to x0, and then I guess the point is if you want to talk about the probability that's between x0 is greater than this and it's less than or equal to x0 plus dx, you can do that. It's basically the probability that x is less than or equal to x0 minus, or x0 plus dx0. So that area equals the probability that sorry, not minus, or it's minus the probability of x over x is equal to x0. So it's basically the difference between, here's say x0 and this point here, dx0 over, or we could say dx0 over that point. That area is the probability. And you can actually say that in terms of this definition of saying, oh, the probability that a particular point, a particular random variable has a value less than another, if you take the notion of a probability mass function and talk about something about the impulse function. Have you guys talked about the impulse function?
No.
Okay. So the impulse function tells you that it's basically infinite at a particular point. In this case, it would be 0. If we brought it to x0 here, let's say, then it's at x0 and it's 0 everywhere else. That's part of the description, and that's where the next part of the description comes through, which is that the integral of x minus x0, that's equal to 1. If from minus infinity to s, that's equal to 1 for s greater than x0, and 0 for s less than or equal to x0 for less than x0. And the point here is that if we take that notion and we say that in the case of our probability mass functions, that we have little impulse functions here, like at 0, 1, 2, 3, like for that example before, this notion about where I was sort of talking about integrals of it's a good way to put it. I guess it fits well into that framework because I can take this, translate it into multiplying each of the values in a particular space with p of x, if this is x, and saying, oh well, multiply each of those by a impulse function at that point with the area scaled by the probability. Then you can start talking about the probabilities in terms of a probability density function, where you can say that the probability that the probability that x is less than 3, less than or equal to 3, is the integral from here to there of those impulses, and it gets convenient to think about that. So it's the same. Oh.
I have no idea what you just said.
Okay.
What is the impulse function?
The impulse function is a mathematical tool, or a way of trying to talk about a point. It's kind of like the notion of a point mass, which is that here's a mathematical way of describing a function that allows us to take this discrete thing and turn it into a continuous thing. And so we had a discrete set of probabilities associated with particular points. And if we want to start talking about the probability density functions, then it's sort of like we want a tool that tells us, well, at a particular point, the value, like we know that the integral is 1 from 0 to from minus infinity to infinity of a continuous probability density function. And we're trying to take the we're trying to take the discrete stuff and try to stick it in the framework of the continuous